Okay, so now what we're going to do, so we've gone over linear least squares regression. And the idea is that you have residuals delta y, which is equal to your measurement minus your estimate, and you create a cost function, and you want to minimize that cost function, and your estimate is H transpose H inverse H transpose Y. Okay? We assume that Y tilde is H x tilde, and we assume that our measurement, Y bar, is Hx plus V, where V is our model noise. Okay? Now, we also assume that the expectation of V transpose is equal to R, some matrix R. Okay? We then get into weighted least squares regression. And we say, rather than using a cost function where we just have delta y in there, we do delta y transpose delta y, and then our solution x tilde becomes H transpose W, H inverse H transpose W, Y bar. Okay? Then if we let W equal R inverse, our estimate becomes H transpose R inverse, H inverse H transpose R inverse Y bar. Okay? So this is everything that we've done up to this point, and I've got videos on those. So now the idea is, what about a priori estimate? Okay? So remember in the common filter video that I first posted, I assumed that you sort of propagate the model to a point, and you have a variable x, what I'm going to call x tilde minus, which is the model right before the update. So it's, you have, that is the current estimate of your model right there. And I'm going to assume that this is equal to the truth signal plus some noise, W. And again, W is going to be my model noise. Okay? So then what I'm going to write is, I'm going to write that the expectation of W transpose, I'm going to call that capital Q. Okay? From here, what I want to do is, I want my estimate, this is my sort of desired state update law. I want it to be equal to some, I'm going to call it gamma or lambda y bar. So I want to use my measurements, right? But I also want to take into account my previous estimate. So this is what I was saying before in the column update. I have an a priori estimate of my state, and then I also have y bar, which is my truth variable, right? Sorry, my y bar, which is my new estimate. And so I want a way to least squares update my state, where I use my a priori knowledge of my state plus the new measurement icon. And I basically want to do this update every single time I get a new measurement. Okay, and that's sort of what I want to do here. All right, what we do is we have to come up, we have to do an optimization problem again, but we need a constraint. And the reason why we need a constraint is because we need this equation to be satisfied in certain situations. Okay, so the certain situations go like this. If we assume, so I'm going to write this in a different color. If we assume that my a priori measurement is equal to my truth signal, right? x tilde minus is equal to x. And I have no model errors, or sorry, sensor measurements. So in this case, v is 0. It means that y bar is equal to hx. Okay? Yeah, y bar is equal to hx. If I assume v is 0, y bar is equal to hx. If I plug these two equations in here, I get x tilde is lambda hx plus gamma x. And if I factor out the x, I get x tilde is lambda h plus gamma times x. If these are true, I want this update law to collapse to x. So I want this to be x. And the only way for this to be x is for this term here to be identity. So it means that when I do my optimization problem, what I want to do is I want to optimize 1/2 del x transpose del x, where del x is the difference between my truth signal and my estimate. Remember, the residuals for y are my y bar measurements and my estimate. For x tilde, I have no measurements because I'm measuring y. So delta x in this case is x tilde minus my truth signal. It doesn't really matter either way. It's x. Yeah, I have x tilde, but I'm gonna use the same notation there. It's x minus x tilde. So delta x is my truth signal, or truth state minus my estimate. I want to minimize this j here, and I think I left out a weighted term. Yeah, I did, so I need to fix that in my notes. But you're going to have the R inverse here, del x, and then that is my cost function I'm trying to minimize. The problem is that I have a constraint now where I plus I minus lambda h minus gamma equals 0. And so what I want to do is I want to minimize j subject to the constraint I minus lambda h minus gamma equals 0. And so what happens is that you need to use the method of Lagrange multipliers, so you get 1/2 del x transpose R inverse del x plus lambda transpose I minus capital lambda h minus gamma. And you want to minimize this, so you have to take a partial of L with respect to x tilde, and that needs to equal 0. And then you need to take a partial of L with respect to lambda, and that needs to equal 0. When you do that entire derivation, what you end up getting is that x tilde equals h transpose R inverse h plus q inverse. And remember, q is the expectation of my model noise. All of that inverse times h transpose R inverse y bar, I'm going to get rid of this here, plus q inverse x tilde. Okay, so let's take a look at this and see what the heck is going on. Okay, this here is kind of called a Kalman gain update. Just consider this just a constant. H is a constant, R and Q are constants, those are just constant variables, okay? X tilde, and I think that should be x tilde minus, it is. This is your a priori knowledge, okay? Q tilde is the inverse of your model noise, okay? So let's say you think you have a lot of model noise. If you have a lot of model noise, it means your a priori variable is probably wrong. So you make Q really, really, really big. Where Q and R, you don't actually know what those are, so you have to sort of pick those as the controls, as the state estimator. And so if I assume that my model noise is terrible, I'm going to make Q really big. If you make Q really, really big, Q inverse is going to be really small, and this term is basically going to go away. Not to mention Q inverse is just going to go away. And if you look at that, that collapses to this equation here, which basically says just do the weighted least squares estimate based on your sensor. So only believe the sensor. So you sort of have this like sliding scale. If you make Q really, 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 really big, you're going to ignore your model and believe your sensor. Now let's do it the other way. What if we thought our sensor measurements were terrible, and so we thought our our covariance estimate of our error in our measurement was really big? We would make R really, really, really big. If R is really big, it means R inverse is going to be really small, which means this term is going to go away, and what's going to happen is you're going to get Q inverse inverse, right? Which is basically Q. And then Q times Q inverse is identity, in which case you're just going to get X tilde is X tilde minus, which means you perfectly believe your model. So again, you have a scenario where R inverse approaches 0, and that in that sense, X tilde is X tilde minus. That means you believe the model, okay? And then in another scenario, you have Q infinity approaches 0, in which case you have X tilde is the weighted least squares regression solution based on your measurement. And so you have this sliding scale where you can say, like, do I really, really believe my measurement, or do I really, really believe my model? And you can sort of pick Q and R based on that to slide between left and right. This is actually a complementary filter. Okay? It's not a Kalman filter yet because there's no state propagation or covariance estimation, but it is a way to filter your noise. You could take a measurement and then keep that measurement, you could take a measurement and then use that as a zero or hold, and when you get a new measurement, you can say, I'm either going to believe my model or I'm going to believe my new measurement that I got. And you can sort of do a complementary filter based on that. Do I believe my past measurement or do I believe my new measurement? And you can kind of do a complementary filter on that. Okay? And this sort of sets open the door for what's called a sequential linear least squares regression. And so in the next video, I'll talk about sequential least squares regression. Okay? If you have any questions, post in the comments, and hopefully this helped you out a little bit.